Okay, today we're going to talk about work. In physics, work means something very specific. It does not mean how much you exert yourself or how tired you get. Is not how you can measure how much work you've done. Okay? You can put in the exact same amount of exertion or force as another person, but do much less work than them. Okay? Because here's what work means. First of all, let's say you have that object there, that square. And let's say I apply a force to that square. And we'll call this force F. And let's say that that force is going in this direction there. Okay? It's not 100% horizontal, but I mean for that to be horizontal there. Okay? So let's call that force F. Okay? And suppose that that force causes the object to move. Let's draw what you call a displacement vector, which means a vector that shows how the object was moved. Let's say the object moved this far. Okay, and we will call that vector D for displacement. Okay, the definition of work would be, in this particular case, the definition of work would be the magnitude of the force I applied times the magnitude of the distance the object moved. Okay? Now let me ask you a question. What is this? What kind of object is this? In this class we deal with two kinds of objects all the time, intermingled with each other, and those two kinds of objects are vectors and scalars. So what is work? Is work a vector or a scalar? Well, the magnitude of F is a scalar, and the magnitude of D is a scalar, and when you multiply two scalars together, you get a scalar. So work is a scalar, not a vector. Okay? It's a number. What are the units of work? Let's write that down. The units are commonly one of two. All right, if you're using the metric system, then the strength of a force, the magnitude of a force, would be measured in newtons, and distances would be measured in the standard unit there is meters. Okay, and so in that case, in the metric system, work is measured by what's called Newton meters, because you're multiplying a number of newtons times a number of meters, and so you get what's called Newton meters. Okay? If you're using the, I guess you call it the standard English system, I suppose. I don't know. I think that's weird because they don't use it in England, but in that case, the magnitude of a force is usually measured in pounds, and distances are usually measured in feet. So what do you think you would get there? For the units, you would get pounds times feet. Now, the normal convention is to not call those pound feet. We usually call them foot pounds. Okay? All right. So it's really easy to measure work. Here's the catch though, if the force is in the same direction that the object moves, or let me say it this way, if the object moves in the direction of the force, then you just multiply the strength of the force times the length of the movement. Okay, but here's the catch. That's oftentimes not the case. In most situations, an object moves in real life in a direction that is not the same as the force that's causing it to move. It sounds weird, doesn't it? Let me explain why that's usually the case. Let me draw this time the force going like this. If you're moving something that's really big and heavy, let's erase this stuff, okay? And let's draw the ground here. And let's draw you. If you're moving something that's big and heavy, isn't it normal that you, well, those are really long arms, but nonetheless, isn't it normal that you don't necessarily push exactly horizontally? Look how that little guy's pushing that big box. Look at the angle of his arms. Okay? He's pushing in the direction of that purple vector. But the box is not going to move up into the air, is it? And why not? Because of gravity. So gravity is usurping some of that little guy's force. Part of his force is going up and part is going horizontal. Didn't we talk about that before? That you can decompose any vector into orthogonal components. So let's see, let's choose blue here. So here's the horizontal component of his force there. And there's the vertical component. The vertical component is being canceled out by the force of gravity pulling down. And that's what's keeping the box from, that's what's keeping him from pushing that box up into the air. In other words, the vertical component of his force is doing no work whatsoever. It's being wasted. Now don't worry about the friction of the box sliding on the ground. We're not talking about that situation. We're assuming here that this is frictionless, okay? Not because I'm wanting to avoid it, just because that's not the topic that we're dealing with. And that has nothing to do with the work, okay? So the only part of his force that's doing any actual work is the horizontal part. Let's erase the vertical component of his force since it's being canceled out. I'm not saying it doesn't exist. I'm just saying it's not doing any work, and we're talking about work, so I'm going to erase it. Okay? Now here's what's interesting is that blue vector is parallel to the red one. They're in the same direction. What's that blue vector called? I think you know from a previous lecture. Isn't that blue vector called the projection of F onto D? And based upon what I said earlier, wouldn't we conclude that the work is equal to the magnitude of that vector times the magnitude of D? Correct? All right, now let's remind ourselves of how to calculate this vector right here. Okay, I'm going to remind you. The projection of F onto D is equal to a number, or if you prefer, a scalar, times vector D, and that's because it's parallel to D, so it has to be a multiple of D. But what is this number? That's the question. Let me remind you that that number is, and I think I'm going to need a little more room, so let me move the vector D over a little bit. Okay, so the scalar that goes in front of that is the dot product of F and D divided by the dot product of D with itself. This is from the previous lecture. That's how you calculate the projection of F onto D. Okay, so let's go back to where we're calculating the work then. The work is equal to the magnitude of that. Okay, let's just write that. Times the magnitude of D. Okay. Now, using the properties of magnitudes, this part right here is a scalar, so it can be factored out. And when you factor it out, you get the absolute value of that scalar. Okay, times what would be left inside the magnitude would still be vector D. Can't factor that out because it's a vector. And then we have this other magnitude of vector D. Okay, good. Now, do you remember this? Do you remember that the dot product of a vector with itself is equal to the norm of the vector squared, or the magnitude of the vector squared? So what we have there is we actually have on the bottom of this fraction right here, we actually have the magnitude of D squared. Okay, so we've got the absolute value of F and D, F dot D, I should say, divided by the magnitude of D squared times the magnitude of D squared. Obviously those cancel out. The magnitude of D squared cancel out, and we're left with the absolute value of F dot D. So let's look at that. I will tell you, this is not the complete story. Whoops, sorry. I wrote magnitude symbol when it should have been absolute value, because F dot D is a scalar, not a vector. Okay, now, there's something that is slightly incorrect there. And that is this. what I have written, work equals the absolute value of F dot D. That's not actually what the work equals. That is the absolute value of the work. Work can actually be negative. Okay? If you apply a force to something and it causes that object to move in a direction opposite of the force, then we say that that force is doing negative work. It's a little bit hard to think of an example in real life where that would happen, but nonetheless, it is possible for that to happen, and in that case, you would say it's doing negative work. Well, this number here is never negative, right? It's an absolute value. So what I have here, the absolute value of F dot D, isn't actually work. It is the absolute value of work. So then you ask this question. If that's the absolute value of work, then what is actually the work? And the answer is, the work is F dot D. That's the work done. Okay? And that might be positive or negative. And here's important for you to understand. You don't have to figure out if it's positive or negative. You just calculate F dot D, and it will come out positive or negative. And it'll come out the correct way. The mathematics takes care of itself. All you have to do is to calculate the dot product of the force vector and the displacement vector. And that's work. Okay, so we're going to do one example. Okay, in this example, we have a force of 50 pounds is exerted on a box at an angle of 30 degrees above horizontal. Okay? And that force causes the box to move from the bottom of that ramp to the top of the ramp. And the ramp spans a horizontal distance of 15 feet. And it rises 3 feet. Okay? So you have your force vector right here. It's already in the picture, so I won't bother drawing it. Okay? You have your displacement vector. Right here. That's our displacement vector. Let's make it a little bigger, we can see it better. Okay, we want to find the work done. Now we don't actually have to find the projection of F onto D because we came out with a very simple formula. Using that projection, we used that as a tool to come up with a very simple formula for work. And now when we want to calculate the work, all we have to do is use that simple formula. And what was the formula? It was work done by F equals the dot product of F with the displacement vector D. All we have to do is calculate that. Okay, so let's find F and D. Let's do D first because D is super easy to find because it goes over to the right 15 and up 3. So let me show you something here. So D is the sum of that vector plus this vector. And what are those two vectors? This part's easy. The horizontal one is the vector 15, 0. And the vertical one is the vector, here, let me actually write that up here. Okay, and the vertical one is the vector 0, 3. And D is the sum of those two. So what's that mean? That means that D is the vector 15, 3. Okay, so that part's easy. Now, let's find the vector F. Let's break that up into its horizontal and vertical components, just like we did for D. We're going to do the same idea. Okay, there's the horizontal component. There's the vertical component. Okay, now what are those two? Remember that the magnitude of F is 50, so if we're thinking about this as a geometry problem, I see a right triangle there with one angle of 30 degrees and a hypotenuse of 50. Okay, so how long is the horizontal leg? It has a length of 50 times cosine of 30 degrees, correct? And so that vector down there is going to be, I'm going to blow this up bigger just for the time being so you can see it here. It's going to be 50 times cosine of 30 degrees, comma 0. What's the cosine of 30 degrees? It's 3 root 2, right? So 50 times the cosine of 30 degrees. Oh, I'm sorry. Did I say 3 root 2? I take that back. I meant to say root 3 over 2, of course. So when I multiply 50 times the cosine of 30 degrees, I get 50 times root 3 over 2. And so what's that going to give me? It's going to give me 25 root 3. Okay, and then we have comma 0. Okay, let's find the vertical component. That's going to be 0, comma 50 times sine of 30 degrees. What's the sine of 30 degrees? It's a half. So we get 0, comma 25. And F is the sum of those two. So F equals the vector 25 root 3, comma 25. Okay, now we can find the work very easily. It's F dot D. So that's going to be the dot product of the vector 25 root 3, comma 25 with the vector 15, 3, which, remember how dot product works. That's going to give us 25 root 3 times 15 plus 25 times 3. So we're going to get 375 root 3 plus 75. That's how much work is done. What are the units here? Think about that. It's going to be foot-pounds, right? And that's the answer to our question. the force does that much work. Okay? Now it's interesting just to point out, you can do a whole lot of force and zero work. What if you had a box sitting on the ground? Let's just look back at our original picture. What if you had that situation? And what if you stood on top of the box and pushed down on it? Then you would be doing a force like this. Would the box move? It would not move, would it? So there would be, the displacement vector would be the zero vector. And so F dot D would be the number 0. And so you would be doing zero work. So you see, it's important to understand that the amount of work you do by the physics definition of work is not the amount of work you do by the definition that you have thought of work all your life as the amount of work I do, is equal to the amount of effort that I put in. That's not true. You can put in tons of effort and do zero work. Okay? All right, that's the end of this lecture.